acid. Now, if amino acids are the monomers, the building blocks of protein polymers, we need to see how they can bond. Now, they bond via condensation reactions. Just like the polymers in the very first unit, just like disaccharides, just like all your condensation polymers, we're going to see that amino acids also condense to form dipeptides, tripeptides, polypeptides, and ultimately proteins. There's a schematic representation there. Let's have a bit of a closer look. Here is a carboxylic acid group that is bonded to an R group that is most likely the rest of an amino acid. On the right-hand side of the screen, you've got an amine group that is bonded to what is most likely another another amino acid. So if you think about it, Ra here is going to represent an unknown amino acid A, and R to the B is going to represent another unknown amino acid. What we'll see happening is the following. The hydroxide group on the carboxylic acid, down the bottom left, reacts with just a single H on the neighbouring amine group. This allows H2O to condense and a new bond is formed. Now the new bond allows a neighbouring amino acid to join to its neighbouring amino acid to form a peptide bond. Have a look on the right where the arrow's pointing. The doubly bonded oxygen is now completely vertical at right angles due to the interactive forces of the neighbouring electron clouds. And likewise, the hydrogen has been forced up at a full 90-degree angle. The OH and the H have combined to form water down the bottom, and there's a single bond between the C and the N. Let's have a look now at the formation of a dipeptide. Here's a carboxylic acid group from one neighbouring amino acid. The doubly bonded oxygen slides up to 90 degrees. Here's an amine group from a different amino acid. The H slides up to 90 degrees. Water is condensed off, and a new bond forms between the two. This bond is called a peptide bond, and you must be able to recognise a peptide bond. It's that bond between the C doubly bonded to the O and the N singly bonded to the H of neighbouring amino acid monomers. A dipeptide is the compound formed when two amino acids react together. The bond between them is called a peptide bond. Dipeptide, therefore, means two peptides, but if you think about it, there's only one peptide bond between those two neighbouring amino acids. So dipeptide does not mean there's two peptide bonds. It means that a peptide bond has been formed between two amino acids. That can be slightly confusing if you're not fully understanding the concept. Let's go and have a look now. This bond here is where the money is. C doubly bonded to an O, N singly bonded to an H, and if Ra and Rb fulfill the requirements of amino acids, so you'd have another centralized carbon with a hydrogen, and then on the left-hand side you'd have an amine group, and on the right-hand side you'd have a carboxylic acid group, you would have a dipeptide. You must be able to recognise the peptide bond. Whenever you see it, you should know that you're dealing with amino acids bonding to form dipeptides, polypeptides, and ultimately proteins. So get that into your memory. Here's another way of representing it. Simply CO and NH. This condensed structural formula is not as immediately obvious, so you need to be able to recognise it as well. Alright, let's have a look now at a real-life representation of the polymerization of amino acids to form a dipeptide. This dipeptide will eventually be called alanine cysteine. That name comes from the parent amino acids. On the left you have alanine, a very simple amino acid. Note the amine group to the left, the centralized CH, an R group, it happens to be methyl, and the carboxylic acid on the right. When that comes into the localized vicinity of cysteine, Cysteine qualifies as an amino acid. Find the amine group, the centralized carbon group, the R group that contains carbon, and the carboxylic acid group. When that amine group on cysteine lines up with the carboxylic acid group on alanine, we can condense it to form a dipeptide. The result would be the formation of the dipeptide alanyl cysteine. There it is. In case you missed that, let's go back. Ready? Up the top, alanyl cysteine. Can you see the peptide bond? It's up the top. You can see the C doubly bonded to the O and the N singly bonded to the H. The rest of cysteine is to the right of that N. The rest of alanine is to the left of that C double O. Note also to the right of screen you have a water molecule, therefore this is a condensation polymerization reaction. Now alanyl cysteine as a dipeptide still has a COOH on the right and an amine all the way over on the left, so there's no reason why this couldn't condense further with another amino acid to form a tripeptide, and this is exactly what happens. We call these end functional groups, the carboxylic acid and the amine groups, terminal groups. If you've been on a train before and it says that this train terminates at the next station, it means that the train ends at the next station. So a terminal carboxylic acid and a terminal amine means that these guys are sitting on the end of the molecule. Because they have terminal COOH and H2N groups, these can further react via condensation to form a tripeptide. Let's have a look. There's my terminal amine. Here's my terminal carboxylic acid. If I bring another amino acid into the vicinity, it could have been to either of those two ends, but let's just use the right-hand end of alanyl cysteine. Can you see how the OH on the carboxylic acid group could easily condense with one H on the amine group to condense a water molecule and form another peptide bond? Here it is. See now the peptide bond in alanyl cysteine and a new peptide bond with the neighbouring amino acid. We still have two terminal carboxylic acid and amine groups, so it could react further, and we've condensed a water molecule to the right of screen. We've polymerized a dipeptide to a tripeptide. This now allows us to form a polypeptide. Due to the presence of terminal amine and carboxylic acid groups on tripeptides, more and more amino acids can continue to join via condensation. This Year 12 can go on infinitum. This is how we form incredibly large, complex, for example, fibrous proteins. Now, a polypeptide simply means many peptides, many peptide linkages forming these big, long proteins. So polypeptides are really just polymers of amino acids. They form very long chains via condensation reactions. Amino acid monomers are really tedious to draw. Can you see how tedious it is to simply draw a di or tripeptide? So, like all good chemistry, we tend to abbreviate them, and we tend to abbreviate them using the first few letters of their names. Now, there are 20 very common amino acids of interest to chemists. They tend to deal with 20 common ones. And there's a three-lettered abbreviation scheme. So let's have a look. Here's a couple of examples. Alanine tends to be referred to as ALA. Alanyl cysteine would therefore be ALA-cis. ALA-cis-ALA, glyphe, ALA-cis, ALA-lys, off we go. It's the first few letters of the amino acid monomers. Now, proteins, therefore, are polypeptides formed from hundreds to thousands of amino acid monomers. And they're all joined via peptide linkages. So they're incredibly complex molecules. And the general formula for the process is this. You have an amino acid bonding. Can you see the condensed structural peptides there? How many can you see? Infinitum with R groups that may be the same or different. Those R groups labelled R1, R2, R3, R4, R to the N are all kinds of different side carbon-containing groups on the basic centralized amino acid group. The difference in those R groups is incredibly vast, and therefore there are any number of different proteins that can be formed in this manner. Those R groups might be polar, non-polar, ionizing polar, and non-ionizing polar. Incredible complexity that will give rise to an incredible structure that we'll examine shortly. There's some terminal amine and carboxylic acid groups, which means that this representation could continue to react further to form an even greater polypeptide. Now here's just some examples of the different forms, again, of amino acids from your textbook. Just 9 examples, and if you examine that closely, again, you've got the examples of non-polar R groups at the top, polar R groups in the middle that form ions by gaining or losing protons, and then the polar groups that don't tend to form ions. Now,